Hello. In this video, we're going to take a look at the concepts of refraction, reflection, Snell's Law of refraction, which helps to analyze the concept of refraction, the concept of the index of refraction and what it pertains to, what variables it depends on, and total internal reflection, which is a very special case of Snell's law and refraction. So let's begin by taking a look at a concept called optical density. Refraction is all about the bending of light as light travels through a medium. Okay, you might notice something in that sentence that I used as a definition there. Bending of light, so light is going to change its path as it passes through a transparent medium. So we need to make sure we understand what the word transparent means and what the word medium means, and we're going to address that shortly. But we can say that the refraction depends on what are called the different optical densities of media. Media is plural for medium. We'll talk about what a medium is shortly. Optical density refers to transmittance. You can think of optical density as a resistance to how light is passing through a particular medium. And the transmittance of light through that medium. Okay, a medium is just an object. It's a material, whatever. It's a something like air, or water, or glass, or plastic. Medium is a material. So the transmittance would be how light is traveling through that material, right? And it's a measure of the intensity of incoming light as a ratio to the intensity of transmitted, that means outgoing light. You could also refer to optical density as it relates to the absorbance. The absorbance of light, okay, of a particular object. All right, so let's talk about some basic definitions here. Transparent means we can see through it, invisible, so to speak. Opaque means we cannot. A medium means any material, anything. A normal means a line perpendicular to a surface. So when I talk about a normal line, I'm talking about the word normal means perpendicular. Okay, let's take a look at how this looks visually. Okay, the first one would be addressing what is called the law of reflection. The law of reflection states that theta 1 equals theta r. Now, what are theta 1 and theta r? We probably should address these. Theta 1 is this incoming angle. So this here is the surface. So let's address all the parts of this picture. Here's the surface. This is the normal. This line right here. This is the incoming ray of light. This is an incoming ray of light. This would be referred to as the incident ray. This ray of light would be referred to as the reflected ray. This ray that bent a little bit as it passed through the surface, this would be the refracted ray. But let's focus on reflection for the moment. Theta 1 is the angle between the incident ray and the normal. Theta 1 is referred to as the angle of incidence. And let's go ahead and address these down here. Theta 1 is referred to as the angle of incidence. Theta 2, well, that's this angle down here. That would be referred to as the angle of refraction. Theta r is referred to as the angle of reflection. N is referred to as the index of refraction. Okay, sometimes I'll call it the IOR because you know how I love to abbreviate. The index of refraction, we're going to get into it more specifically what it is. Sometimes I'll also refer to it as the refractive index. Just reverse the word around, reverse the term. So what we have here is the law of reflection is stating that the angle of incidence, the angle created with the incident ray and the normal, is exactly the same as the angle of reflection, the angle created between the reflected ray and the normal. This is what the law of reflection tells us. It is true for any reflective surface. The most common reflective surface you're familiar with, of course, is a mirror. There are three types of mirrors we'll study. There are flat mirrors, otherwise known as plane mirrors, because a plane surface is flat. There are also curved mirrors, spherical mirrors that curve inward. Those are concave mirrors. And ones that bend away from you or curve away from you, those are called convex mirrors. And law of reflection applies to every mirror the same way. Okay, and we'll talk about that in our next video. Now, just to get an idea of how light works here, light is traveling from a higher index to a lower index. So when light is traveling from a higher index of refraction to a lower index of refraction, this would be, for example, when light is traveling from, let's say, glass into air. The higher the index of refraction, the more optically dense the medium is. Okay, so air has the lowest optical density of any medium because air is essentially a clear medium. Light passes through unobstructed, doesn't need to bend. Glass, on the other hand, the molecules are a little close together, and because the molecules are a little close together, it absorbs that electromagnetic radiation of the light a little bit differently as the light passes through. Okay, so the closer the molecules are together, the more dense the molecules are together, that's going to affect the transmittance of light through the material. So the higher the index of refraction, the higher the optical density, the slower light will pass through the medium, the more resistive it is to light passing through the medium. Okay, so this is an example, like a light going from, let's say, glass to air. When this happens, light will refract away from the normal. When light passes from a lower index of refraction to a higher index of refraction, it is exactly the opposite. Light will refract toward the normal. And that would be, for instance, let's say going from air into water, or air into plastic, or air into glass, something like that. There is a relationship that binds all of this together. It is known as the Snells Law relationship. And that is where it's a relationship between the indices of refraction between the two media and the angles with which the light is incoming and bending through. Okay, when light approaches the boundary between two media, otherwise known as theta 1, the incident angle, let's go ahead and note that, theta 1. This is the incident angle, or the angle of incidence. A couple ways you could state it. And the angle with which the light bends while passing through the second medium, that would be theta 2. That is the angle of refraction, or the refractive angle. The equation we're going to work with is referred to as Snell's Law. N1 times the sine of theta 1 equals N2 times the sine of theta 2. This equation has four parts to it. This is the first term, N1. This is the second term, sine of theta 1. That's the third term, N2. And that's the fourth term, sine of theta 2. We will practice using this equation to solve shortly. But first, let's dive into the index of refraction. More specifically, what is it about? Well, the index of refraction is the ratio of two things. It's the ratio of the speed of light in a vacuum to the speed of light in a medium. Okay, so let's write that out. The index of refraction, N. We're going to write these over here. So IOR, there's two formulas for index of refraction. N is equal to a ratio of the speed of light in a vacuum, which we're going to call C, to the speed of light in a medium, which we are going to call V. The ratio of speed of light in a vacuum to the speed of light in a medium is one way that we can calculate the index of refraction. But it's also the ratio of wavelengths. Wavelength is the length of where a wave begins to where it repeats again. And the wavelengths of light are really, really small. And the index of refraction represents the wavelength of light traveling through a vacuum. Vacuum would be, no obstruction whatsoever, like through outer space. Okay, and the index of refraction of air is very similar to the index of refraction of a vacuum. So the wavelength of light passing through a vacuum is this variable here, lambda naught. And it's the ratio of the wavelength of light in a vacuum to the wavelength of light in a medium. So there are two equations that satisfy the concept of the index of refraction. Both of them are a ratio of vacuum to medium. The first equation just relates to the speed of light in a vacuum to the speed of light in a medium. The second equation relates to the wavelength of light in a vacuum to the wavelength of light in a medium. Now, total internal reflection is a very, very specific case of Snell's Law application. And it occurs when light approaches a boundary between two media at a certain angle called the critical angle. And it results when light is completely refracting along the surface between two medium. When this happens, the angle of refraction is 90 degrees. Let me show you a picture of what this would look like. Say you had a surface like this, and you had laser light passing through, and let's say this was plastic. Okay, and let's say this was air. And here's our medium. Let's say we were passing laser light through this plastic at some angle theta 1 to the normal. It's going to refract far away from the normal when it passes into air. But when we make this wide enough, what that does is, as we make the angle of incidence wider, we make the angle of refraction wider to the point where it's going to be refracting along the surface. So you can see theta 2 is 90 degrees as we refract along the surface. So starting with the Snell's Law equation, here's what we get. We start with our equation. N1 sine theta 1 equals N2 sine theta 2. But here's what we do. We're going to replace theta 2 with 90 degrees. Now the sine of 90 is 1. So what that effectively does is that changes the equation now to sine of N1 sine of theta 1 equals N2 times 1. But we don't really need the 1 because anything times 1 is itself. When we solve for theta 1, we divide both sides by N1. And then we take the arc sine of both sides. The equation we use is the sine of theta c equals N2 over N1. Where theta c is referred to as the critical angle. Again, theta 1, the critical angle, is the measure of theta 1 when theta 2 is 90 degrees, refracting along the surface. Another thing to note, N1 is always going to be greater than N2. Always. The denominator will always be bigger. And that has to do with the way that we solve an equation. A sine function is never going to be, the sine of any angle is never going to be greater than 1. The highest, the sine of 90 is 1, and you can't get any higher than that. So if the numerator were bigger, you'd have a number greater than 1, and you can't have a sine of an angle greater than 1. So the bottom number has to be greater than the top number in all cases. The angle incident, angle, if you have an incident angle that's larger than this critical angle, it simply just results in only internal reflection. So it's just internal reflection. Now what that would look like this. If we had, let's say, a wider angle coming from here, it would just simply reflect down that way, okay, with no refraction to the other side of the surface. Okay, this is a concept known as total internal reflection. This again occurs when your incident angle, when you produce an incident angle that creates a 90-degree refractive angle, and the refracted ray will refract right along the surface between the two media.